Hello everyone, we are going to discuss question number 54 from MTP3. Here there is a cell given to us which have a potential of 0.55 volt at 25 degrees Celsius, and we can easily see that there are two electrodes. One is hydrogen electrode and the other is calomel electrode. The hydrogen electrode is in anodic side and the calomel electrode is in cathode side, and we have to find out the pH of the solution. So coming to the solution part, first of all we will write down the cell reaction, and we can easily see that the cell potential is given as the cell potential as the half cell potential of hydrogen and the half cell potential of calomel electrode, and the sum is given as 0.55 volt. We know that the cell potential of calomel is 0.28, so the half cell potential of hydrogen electrode will be 0.27. Now we have to find out the concentration of H plus. Then we will need to use the Nernst equation for the half cell reaction taking place in anodic side. We know that in anode side H2 is getting converted into 2H plus and 2 electrons. So applying Nernst equation we will get E equals to E naught minus 0.059 divided by N log of H plus square divided by pressure of H2. Substituting all the values that we are having, 0.27 equal to 0 minus 0.059 divided by 2 log of H plus square, as the pressure of H2 is given 1 atmosphere and the number of electrons that are being transferred in this half cell reaction are 2. Now the only unknown that we have here is H plus. We can write the negative log of H plus as pH, and solving further we will get the value of pH is 4.6. so that is the final answer, 4.6. Hello everyone, we are going to discuss question number 55 from MTP 3rd. Here the rate constant for the decomposition of dinitrogen pentoxide is given at 25 degrees Celsius as well as at 55 degrees Celsius, and we have to find out the rate constant at 35 degrees Celsius. So here we are going to use the relation between temperature and rate constant. As you know that this relation exists as log of K2 by K1 equal to activation energy divided by 2.303 R into 1 by T1 minus 1 by T2. Here first of all we will apply this equation for temperature 25 degrees Celsius and 55 degrees Celsius. So the equation will go like log of 1.7 into 10 raised to the power minus 3 divided by 3.7 into 10 raised to the power minus 5 equal to activation energy divided by 2.303 R into, in brackets we will have 1 upon 298 minus 1 upon 328. Similarly we will apply this same equation for the temperatures 25 degrees Celsius and 35 degrees Celsius. Now dividing the both the equations, we will remove the unknown term activation energy, and the only unknown quantity that will be remaining will be K3. So further solving we can get K3 as 14.3 into 10 raised to the power minus 5. Hello everyone, we are going to discuss question number 59 from MTP 3rd. Here we have to find out the time that would be taken in order to deposit 100 gram of aluminium from an electrolytic cell, and we are using a current of 125 ampere. So now coming to the solution part, we know that from Faraday's first law that the amount that is deposited on passing a certain amount of current is given as W equals to Z into Q. Q is equal to IT and Z is electrochemical equivalent, that is written as M divided by NF. So substituting all the required values in this formula, we will get W, that is amount deposited, 100 gram, molecular mass capital M, that is 27 gram, into current 125 gram and time that is unknown divided by NF. N is valence factor, so valency factor here is 3 as aluminium is going from +3 to 0, and F is Faraday's constant, that is 96500. And from here we can find out the time required to deposit that much amount, that is 8577 seconds. Hello everyone, we are going to discuss question number 60 from MTP3. Here we are given with a decinormal solution that have two platinum electrodes 1.8 cm apart and having area of 5.4 cm square. Resistance of this solution is 32 ohm. We have to find out the specific conductance as well as the equivalent conductance. Now we know that the specific conductance of any solution is given as 1 upon R multiplied by L by A, that is cell constant. So here resistance is given as 32 and L is given as 1.8 centimeter and area is given as 5.4 centimeter square. Substituting all the values, we will get the specific conductance as 0.0104 ohm inverse centimeter inverse. Now to calculate the equivalent conductance, we will use the formula. Equivalent conductance is given as specific conductance multiplied by 1000 divided by normality. Substituting all the values, we will get the equivalent conductance is 104 ohm inverse centimeter square equivalent inverse.